In this video, we're going to talk about the probability that one or another event happens. When we say event in probability, we just mean anything. So what's the probability of one thing happening? And the key here is that we're going to talk about the probability of one or another event happening. There's another video that I have posted about the probability of one event and another event both happening. Here the focus is going to be on or. The more mathematical term for this is the probability of the union of two events. These first two sentences mean the exact same thing. The second one is just the more mathematical way of saying it. One important thing to note, though, is that in math, when we say or, we mean at least one. Meaning it could possibly be both and we'd still be happy about that. And you'll see an example towards the end of the video of what I mean by that. Because normally in everyday life, when someone says you can have one or the other, you cannot have both. But here, or does mean at least one. It could possibly be both. Okay. Now there's two different types of probability involving or, because there's two different types of events. The first type that we'll look at is something that we call mutually exclusive. The definition of that is events that cannot happen at the same time. And that should make sense, but because in everyday language the word exclusive means, it's exclusive. Not everyone is invited. It's to exclude someone. You're not inviting them. You're not including them. And so when we say mutually exclusive, we mean they're both excluding each other. So here we have the probability of A or B happening. And again, when we have this formula here, the P and then the parentheses does not mean multiplication when we talk about probability. This P means, when we look at this P on the outside and then in parentheses just means the probability of whatever is inside the parentheses. So the probability here of A or B happening. That's what this left side means. And we're saying that if the events are mutually exclusive, then the probability of A or B is equal to just the probability of A plus the probability of B. And here's an example here of where this is. It's a pretty straightforward example of why this formula works. So it says if one card is drawn from a standard deck of 52 cards, use cards a lot in probability examples, what is the probability that you get a king or a queen? Now we know that there are 52 cards. It says that in the problem. We also know that there are 4 kings and there are also 4 queens. So if we look at this formula, which you don't necessarily need the formula to do this, so let's hold off on the formula for just 1 second. Because there are 4 kings and there are also 4 queens and there are 52 total cards and I'm only drawing 1, well, there's 8 of those 52 cards that I want. So the probability should make sense to be 8 out of 52. So this is a really simple example of why this formula works, and that's all we're trying to do here, is show a really simple example of this formula. So let's look at it with the formula. So I'm going to use a little bit of shorthand here and say that the probability really is the probability that we get a king, so I'll use K, or we get a queen, so I'll use Q. Now my formula says that that should be equal to the probability of getting a king plus the probability of getting a queen. Look at those two probabilities separately. And again, we just said there are 4 kings out of the 52 total cards and 4 queens out of the 52 total cards. Add those two together and that's 8 out of 52. Just like we intuitively thought that it would be. Again, the purpose of this example is not to really show a complicated example, it's to show a simple example of how the formula works. Then I can simplify this, and that's 2 over 13. And if I wanted, I could turn that into a decimal and say that my probability is approximately 0.154, which if I really wanted, I could turn into a percentage and say this is about 15.4%. And that's an example of this sort of or probability. What's the probability of getting a king or a queen? Now what's important is that these events, getting a king and getting a queen, they are, like we said, mutually exclusive. They can't happen together. Now if we drew more than one card, it is possible for me to get a king and a queen, but again, that changes the word. It would no longer be or, it would be and then we have to look at a different video to explain that. Here it's or though, and it's not possible to only draw one card and get a king and a queen. That one card has to either be a king or a queen or something else, but it cannot be both. So we call this an example of mutually exclusive probability. Together, they exclude each other. Being a king excludes the possibility that it's a queen. Being a queen excludes the possibility that it's a king. So these events cannot happen at the same time, so I just add their probabilities individually, and I get the total probability. Again, this example is kind of a simple one, but it's just to demonstrate the formula, and then you can apply it to more complicated situations. Let's look at the other possibility, that our two events could happen at the same time. The word for that is inclusive. They are including each other. Events that can occur at the same time are called inclusive. Again, we start with, the formula starts the same. Probability of A or B is equal to just the probability of A by itself plus the probability of B by itself. But then this time we subtract away the probability of A and B. The reason we have to do that is because if the two events can occur at the same time, then when I count all the ways that the first event can happen, plus all the ways that the second event can happen, I'm double counting the ones that happen together. And so then I have to just subtract away those ones that happen together, so I make sure that everything is only counted once. And this example here is a nice example to show how that works. So now we're still drawing just one card from a standard deck of 52, and we want to know what's the probability that we get a king or a diamond. Now if you know anything about cards, there are 4 cards of each type, like in the last example, 4 kings and 4 queens. But there are also 4 what we call suits. There are diamonds, there are hearts, there are spades, and there are clubs. There are 13 cards in each suit. An ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, a jack, a queen, and a king. So there is a possibility that I can get a king and a diamond at the same time. There's in fact the king of diamonds. So this is an example of inclusive events because the two things that I want, king or diamond, can occur at the same time. I can get a king of diamonds. So not only do I have to add the probability of a king plus the probability of a diamond, but I then have to subtract away the probability that it's both so I don't double count. So let's look at this here. So start with the left side. We're looking at the probability that we would get a king, or I'm going to do my best to draw a little diamond here, a diamond. We like shorthand in math. So what's the probability of a king or a diamond? Well, this should be equal to the probability of a king plus the probability of a diamond minus the probability of both happening together, which is our AND probability. Which again, if you need a little more work on the AND, look at the video compound probability part 1. So the probability of a king and a diamond. So let's just look at all these three parts and then simplify. The probability of a king, just like in the last example, is still 4 out of 52. The probability of a diamond, like we just said, is 13 out of 52 because there are 13 diamonds in the deck of 52 cards. Then I subtract away the probability that I get both a king and a diamond. Now for this example, it's really easy to figure out the probability that I get both a king and a diamond. There's only one way that that's possible, the king of diamonds. So the probability of that is 1 in 52. And we'll simplify this in just 1 second, but before we do that, I want to talk about why this makes sense again. When I look at my first fraction here, the 4 in 52, that's because there are 4 kings out of the 52 total cards. The 13 in 52 for the diamonds, because there are 13 diamonds and there are 52 total cards. But in this 4, one of those 4 is the king of diamonds. In this 13, one of these diamonds is the king of diamonds. So I've counted it twice. So I have to subtract it away once. I want it to be counted, but not twice. Drawing the king of diamonds just is one of the possible ways that I could get either a king or a diamond. There are several ways I can do it. Drawing the king is one of the ways it could happen. There's nothing special about it. It's still just a king or a diamond in this situation. So I want to only count it once, and so I need to subtract it away. So it only gets counted in one of these two spots, but not both. So now let's simplify. If we take 4 plus 13 minus 1, we'll get 16 out of 52. So there are 16 total cards, or 16 cards out of the total of 52 that are either kings or diamonds. And we've only counted the king of diamonds once. We can simplify that to be 8 in 13. That's right. As soon as I wrote that, I knew that was wrong. It's not 8 out of 13, it's 4. 4 out of 13, so let's just get that out of the way here. It's 4 out of 13. So you've got a 4 in 13 chance, which, if we use our calculator real quick, that should be a little more than, or a little less than about a third of a chance here. So 4 divided by 13 is approximately 0.308, approximately, rounded to the hundredths place there, which is then, of course, still approximately, because I still rounded it, about a 30.8% chance. So to get a king or a diamond, I've got about a 30.8% chance. The most important thing we recognize here is that it is an inclusive union here. These two things can occur together, so not only do I add, but I then have to subtract, so there's no double counting. The most important thing for you to do, if you have a question about one thing or another happening, is deciding first, can these things happen at the same time, or are they mutually exclusive and they cannot happen at the same time? If they're mutually exclusive and they can't happen together, just add the two separate probabilities together. If they're inclusive and they can happen at the same time, add the two probabilities just like for mutually exclusive, but then subtract away the probability that both happen so that you don't double count. But most important, you've got to decide, is it inclusive or is it exclusive? And then there's just that small difference you have to worry about. But mostly for or, you're adding, just adding, and maybe a little subtracting at the end. All right, that is compound probability part 2 with the probability of the union of two events, or when we say one event or another.